Tonight, I want to take you into something that sounds almost too familiar to be interesting. Gravity. You have lived with it your entire life. You have never had to learn it. You never had to study it in school to understand it. You learned gravity the first time you tried to stand up. The first time you dropped something and watched it fall. The first time you jumped and felt the ground catch you again. Gravity feels so obvious that most people assume we already understand it completely. Like it is finished. Like it is solved. Like it is just a basic fact of life. The same way the sky is above you and the ground is beneath you. But here is what most people do not realize. Gravity is the one force in nature that still refuses to fully fit into our best picture of reality. And the more carefully you look at it, the stranger it becomes. Not because it stops working. Gravity works incredibly well. It works so well that we can predict where planets will be years from now. We can predict how a spacecraft will swing past a planet and steal a little bit of speed from its motion. We can predict how starlight bends as it passes a galaxy. We can even detect tiny ripples in space-time caused by massive objects colliding far away. Gravity is reliable. It is consistent. It is everywhere. And yet, it behaves differently from everything else we know. To understand why, start with something simple. Think about how you normally imagine a force. If you push a door, your hand touches the door. If a magnet pulls a piece of metal, you picture the magnet doing something through space, like an invisible thread. If you turn on a light, you picture energy flowing through wires, through a system, through something that connects cause and effect. Now think about gravity in everyday life. You hold your keys in your hand. You open your fingers, the keys fall. Why? You can say the word gravity and move on. But if you stop and really ask what is happening, you realize something strange. Earth is pulling on those keys. The Earth is not touching them. There is no rope, no arm, no visible connection. And yet the keys fall every time with the same calm certainty, as if the universe has a rule written into it. That basic mystery has been with us for a long time. In the 17th century, Isaac Newton figured out a way to describe gravity with mathematics. His law worked. It explained falling objects and planetary motion with the same simple relationship. That was a turning point in human history. Suddenly, the heavens and earth were not separate realms. They were governed by the same physics. Newtonian gravity is still incredibly useful. It is still used for most space navigation. It is accurate for everyday conditions and even for many conditions in the solar system. If you want to predict how a satellite moves around Earth, Newton gets you very far. But even Newton did not feel satisfied by what his own equation implied. His law treated gravity like a force reaching across space instantly. A planet pulls on another planet without delay. The sun pulls on Earth across the vast emptiness between them. The effect is immediate in the equation. Newton did not like that. And he had a point. Instant action across empty space does not feel like a complete explanation. It feels like a rule that works, but a story that is missing a mechanism. 2 centuries later, Einstein changed the story completely. Einstein said, "Gravity is not a force reaching outward. Gravity is the shape of space-time itself. Space and time are not just a passive stage where events happen. They are part of the physical system. Mass and energy change the geometry of space-time. And that geometry tells objects how to move. In this picture, the Earth is not pulling your keys with an invisible hand. The Earth changes the structure of space-time around it, and your keys follow the natural path in that curved structure. That path looks like falling. This sounds like a strange way to talk about something as basic as dropping keys, but it makes predictions that Newton could not make, and those predictions have been tested. Einstein's theory explains the small extra shift in the orbit of Mercury that Newtonian gravity could not account for. It predicts that light bends near massive objects because light travels through curved space-time. That effect has been measured many times. It predicts that time runs differently depending on gravity, that clocks tick at different rates at different heights. That is not philosophy. It is measured. It even matters for practical technology, like satellite timing systems. And perhaps most famously, the theory predicts gravitational waves. Not waves moving through space, but waves of space-time itself. Those waves were detected directly in the early 21st century, exactly in the way general relativity predicted. So far, general relativity has passed every serious test thrown at it. At this point, it is tempting to say the problem is over. We have the theory, we have the evidence, we have the precision. Gravity is understood. But the real problem appears when you zoom in, not outward. Because general relativity is not a quantum theory. It is a classical theory. It treats space-time as smooth, continuous, like a fabric with no threads, no pixels, no grain. Quantum mechanics does not work that way. Quantum physics tells us that nature at small scales behaves in discrete, probabilistic ways. Fields have fluctuations. Energy comes in quanta. Particles behave like waves. Reality is not smooth at the deepest level, at least not in the way classical physics imagines smoothness. Every other force in nature has been successfully described using quantum mechanics. Electricity and magnetism are quantum. The strong force that binds atomic nuclei is quantum. The weak force that governs certain kinds of decay is quantum. These forces can be described with quantum field theories that have been tested to extreme accuracy. Gravity does not slide neatly into that framework. When physicists try to treat gravity the same way, the calculations blow up. Not in a small way, in a fundamental way. The mathematics produces infinities that do not behave like the manageable infinities that can be handled elsewhere. The theory stops being predictive in the usual sense. This does not mean gravity cannot be described quantum mechanically. It means the most straightforward method, the method that works for the other forces, does not work cleanly for gravity. And the reason is not just technical, it is conceptual. In quantum field theory, you normally assume space and time as a background. Fields live in space-time. Particles move through space-time. You build the theory on top of that stage. But in general relativity, space-time is not a fixed stage. It is dynamical. It bends. It evolves. It responds to energy and momentum. It is part of the system. So trying to quantize gravity is not like quantizing a field on a stage. It is like trying to quantize the stage itself. That is the central tension. Two of the most successful theories ever created describe reality in two different languages. Each language works beautifully in its own domain. But when they overlap, when you need both at once, the combined picture becomes incomplete. Where do you need both at once? In places where gravity is strong and the relevant scales are small. Near the centers of black holes. At the earliest moments of the universe. In situations where space-time might be forced into extreme conditions, where the idea of smoothness becomes questionable. This is why gravity feels different. Not because it is weak or common, but because it sits at the boundary between our best ideas. It is woven into the structure of space and time, and that makes it unlike the other forces from the very beginning. And once you see that, a new kind of question starts to feel reasonable. Not a wild question, not a mystical one, but a careful one. What if gravity is not fundamental in the same way the other forces are? What if it is more like a macroscopic effect, something that emerges when many microscopic degrees of freedom act together? The way pressure emerges from molecules, the way temperature emerges from motion, the way a wave emerges from countless water particles moving in coordinated patterns. That idea might be wrong. It might be incomplete. It might apply only in special cases. But it exists for a reason. It exists because gravity has earned the right to be questioned in a different way. And to even talk about that possibility responsibly, we need to introduce a concept that most people associate with heat, not with gravity: entropy. Not as a metaphor, not as a vague idea about disorder, but as a precise physical quantity, that measures how many microscopic possibilities can hide beneath a single visible reality. If gravity were just another force, this is where the story would end. We would look for the right particles, write down the right equations, and slowly refine the details. That approach worked for everything else. But gravity keeps pointing in a different direction, and the clue has been there for longer than most people realize. To see it, we have to step away from planets and falling objects for a moment and look at how physics understands large collections of things. Take something simple, like air in a room. You cannot see the individual molecules. You do not track their paths. Yet you can still talk about temperature and pressure as real physical quantities. Temperature tells you how much microscopic motion is hidden inside the air. Pressure tells you how often those molecules collide with the walls around them. These quantities feel fundamental, but they are not. They emerge from the collective behavior of many unseen parts. Entropy belongs to this same category. In everyday language, entropy is often described loosely, sometimes as disorder, sometimes as chaos. That language is catchy, but it hides what entropy really is. In physics, entropy has a precise meaning. It measures how many microscopic arrangements correspond to the same large-scale state. Imagine you have a box filled with gas. You do not know the exact position and motion of every molecule, and you do not need to. Many different microscopic configurations all look the same at a large scale. The entropy counts how many of those hidden configurations are possible. This idea goes back to the work of Ludwig Boltzmann in the 19th century. He showed that entropy is not about messiness. It is about counting. It is about how much hidden information fits beneath what you can observe. Once you see entropy this way, something important changes. Entropy is no longer just about heat. It becomes a bridge between microscopic physics and macroscopic behavior. It explains why some processes happen naturally in one direction, but not the other. It explains why time seems to have an arrow, even though the basic laws of physics do not clearly prefer past over future. And surprisingly, entropy also appears in gravity. This is not obvious at first. Gravity feels geometric. It feels smooth. It feels like it should have nothing to do with counting microscopic states. But when physicists studied black holes, entropy appeared in a way that no one expected. Black holes are extreme objects. They form when matter collapses so densely that not even light can escape. For a long time, they were thought of as simple. According to general relativity, a black hole can be completely described by just a few numbers: its mass, its rotation, and its electric charge. Everything else about the matter that fell in seems to disappear. That simplicity raised a problem. If entropy measures hidden microscopic possibilities, then a black hole should have very little entropy. After all, it seems to forget almost everything about what formed it. But that conclusion turned out to be wrong. In the 1970s, physicists discovered that black holes behave like thermodynamic objects. They have a temperature, they emit radiation, and most surprisingly, they have entropy, a lot of it. The entropy of a black hole is not proportional to its volume. It is proportional to the area of its event horizon, the surface beyond which nothing can return. This was shocking. In ordinary systems, entropy scales with volume. More space means more room for microscopic arrangements. But black hole entropy scales with surface area instead. This was not a metaphor. It came out of precise calculations combining general relativity, quantum field theory, and thermodynamics. The results suggested that the information content of a region of space might be encoded on its boundary, not throughout its interior. That idea did not come from philosophy. It came from mathematics that refused to give a different answer. At this point, the connection between gravity and entropy stopped looking like a coincidence. It started to look like a hint. If gravity is tied to space-time geometry, and space-time geometry is tied to entropy in extreme situations, then perhaps gravity itself has a thermodynamic aspect. Perhaps the smooth geometry we see, is an effective description, like temperature, emerging from something more microscopic. This does not mean space-time is made of tiny pieces in a simple way. It does not mean gravity is fake or illusory. It means that what we call gravity might be a large-scale description of deeper degrees of freedom we do not yet fully understand. The key point is not that this idea is correct. The key point is why it exists at all. It exists because gravity behaves like no other force, and because entropy keeps appearing in places where it was never expected. Once entropy enters the picture, a new question becomes unavoidable. If entropy counts hidden information, then what information is being counted when space-time curves? Where is it stored? And why does the universe seem to respect limits on how much information can fit into a region of space? Those questions do not lead immediately to answers, but they lead naturally to a principle that reshaped theoretical physics. A principle that says the universe may allow far less information than our intuition suggests. The idea that information might be limited by surface area rather than volume feels deeply counterintuitive. In everyday life, if you have a bigger box, you can store more things inside it. If you double the size of a room, you expect to be able to fit roughly twice as much furniture. Our intuition is built around volume. Space feels like something you fill from the inside out, but gravity keeps pointing in another direction. The clue comes from black holes, but it does not stay there. Once physicists accepted that black hole entropy scales with area, they began to wonder whether this was a special property of black holes or a more general feature of space-time itself. If a black hole represents the maximum possible entropy that can fit into a region, then perhaps there is a fundamental limit to how much information any region of space can contain. This idea did not appear suddenly or dramatically. It emerged slowly as researchers tried to make sense of calculations that refused to behave in familiar ways. Again and again, the mathematics suggested that trying to pack too much information into a region of space leads inevitably to gravitational collapse. Push hard enough, and the region becomes a black hole. At that point, the amount of information you can access is determined by the area of the boundary, not the volume inside. What makes this unsettling is what it implies about space-time. If information is limited by area, then the smooth three-dimensional space we experience might not be storing information in the way we instinctively imagine. The bulk of space may not be where the fundamental degrees of freedom live. This line of thinking led to a simple but radical proposal. The physics inside a region of space might be fully described by information encoded on its boundary, not symbolically, not approximately, but exactly, at least in certain theoretical settings. This proposal became known as the holographic principle. The name is evocative, but it can be misleading. It does not mean the universe is an illusion or a projection in the everyday sense. It means that the maximum amount of information that can exist in a region of space grows like the surface area surrounding that region, not like the volume it encloses. The principle was not invented to sound clever. It was an attempt to resolve real contradictions between gravity, quantum mechanics, and thermodynamics. Without such a limit, the theories clash in ways that cannot be ignored. What is striking is how conservative the logic actually is. No new particles are assumed. No exotic dimensions are required at this stage. The argument comes from combining known physics and asking what happens when its implications are taken seriously. If gravity enforces an upper bound on information, then space-time itself may be constrained in a way that has nothing to do with distance alone. The geometry we measure may be an effective description that emerges when many microscopic degrees of freedom are averaged together, much like temperature emerges from molecular motion. This perspective reframes the original problem of gravity in a subtle way. Instead of asking why gravity refuses to behave like the other forces, we can ask whether gravity was ever meant to be treated the same way in the first place. Perhaps gravity is not a field living in space-time. Perhaps it is a reflection of how information is organized. That idea remains theoretical. It is not confirmed by experiment. It does not replace general relativity, which continues to work extraordinarily well, but it changes the questions physicists ask. Instead of searching only for a quantum particle of gravity, they also ask how space-time itself could arise from deeper principles. At this point, the path forward becomes clearer. To understand whether gravity could emerge from entropy, we need to understand entropy not just as a property of matter, but as something tied to space itself. We need to explore how information behaves in gravitational systems, and why black holes seem to sit at the boundary of what physics allows. Those questions lead directly into the heart of modern theoretical physics, where gravity, thermodynamics, and quantum information begin to overlap. And it is there that the idea of space-time as an emergent structure takes its most precise mathematical form. Entropy is a word most people recognize, but almost no one is comfortable with. It shows up in school textbooks, in popular science, and sometimes even in everyday conversation. It is often described loosely as disorder, as randomness, as things falling apart over time. Those descriptions feel intuitive, but they miss what entropy actually means in physics. To understand why entropy matters for gravity, we need to slow down and strip the idea back to its most basic form. Imagine something familiar, a deck of cards. When the cards are new, they often come ordered, suits grouped together, numbers in sequence. If you shuffle the deck thoroughly, the cards look random. Most people would say the shuffled deck has more entropy. That intuition is not wrong, but it is incomplete. The real reason the shuffled deck has higher entropy is not because it looks messy. It is because there are vastly more ways for the cards to be shuffled than there are ways for them to be perfectly ordered. The ordered state is special, rare, fragile. The shuffled states are common, numerous, easy to reach. Entropy, in physics, is a way of counting how many microscopic arrangements correspond to the same large-scale description. This idea becomes clearer when we move from cards to something like gas. Picture a sealed box filled with air. The air spreads out evenly, filling the entire volume. That is the state we expect. But there is nothing in the laws of motion that forbids all the air molecules from drifting into one corner of the box. That configuration is allowed. It just never happens. Why? Because there are unimaginably many ways for the molecules to be spread evenly, and almost no ways for them to all cluster in one corner. The evenly spread state has far higher entropy, not because it is more chaotic, but because it corresponds to more microscopic possibilities. This was the insight of 19th century physics, made precise by Ludwig Boltzmann. Entropy is proportional to the number of microscopic states that give rise to the same macroscopic appearance. The more hidden configurations there are, the higher the entropy. Once you see entropy this way, several things fall into place. You understand why heat flows from hot objects to cold ones. There are more microscopic arrangements where energy is spread out than where it is concentrated. You understand why gases mix and never unmix. You understand why time seems to have a direction, even though the fundamental equations of motion do not clearly distinguish past from future. Entropy is not about what must happen. It is about what is overwhelmingly likely to happen. This distinction matters. The laws of physics do not forbid the air in a room from gathering in one corner. They simply make it so unlikely that it will not happen within the lifetime of the universe. Entropy does not impose absolute rules. It imposes statistical ones. For a long time, entropy was associated almost exclusively with heat and energy flow. It belonged to thermodynamics. Gravity lived somewhere else, in geometry and motion. The two subjects seemed unrelated. That separation turned out to be an illusion. When physicists began studying extreme gravitational systems, especially black holes, entropy appeared in a place no one expected, not as an analogy, not as a poetic comparison, but as a precise quantity, obeying mathematical laws. That discovery forced a rethinking of what entropy actually applies to. If space-time itself can have entropy, then entropy is not just a property of matter inside space. It may be tied to space itself. This is a radical shift, and it needs to be handled carefully. Before we can connect entropy to gravity, we must be clear about what entropy is and what it is not. It is not a measure of ignorance. It is not a subjective quantity. It does not depend on human knowledge. Entropy is objective. It counts real physical possibilities, whether or not anyone is aware of them. That objectivity is what makes entropy powerful. It allows us to bridge scales from microscopic motion to macroscopic behavior without invoking intention or purpose. It explains why large systems behave predictably, even when their individual components behave unpredictably. And it is precisely this ability to bridge scales that makes entropy relevant to gravity. If gravity is tied to the large-scale structure of space-time, and entropy encodes the collective behavior of microscopic degrees of freedom, then understanding entropy becomes essential, not as a metaphor but as a tool. In the next step of this story, entropy will stop being an abstract counting device and start becoming something geometric, something that scales with area, something that challenges our intuition about where information lives. But for that connection to make sense, we must first stay grounded in what entropy actually is: a measure of possibilities, a bridge between levels of description, and a quiet guide that tells us which states of the universe are likely and which are not. Once entropy is understood as a way of counting possibilities, not as a vague idea about disorder, its role in physics becomes much clearer. It stops being mysterious and starts being practical. It becomes a tool that tells us how likely certain outcomes are when many small parts act together. Consider something simple again: a cup of hot coffee left on a table. Over time, it cools down. Heat flows from the coffee into the surrounding air. Everyone expects this. But the laws of motion that govern the molecules in the coffee and the air do not actually forbid the reverse process. In principle, energy could flow from the air back into the coffee, making it hotter on its own. That never happens. Not because it is impossible, but because it is unimaginably unlikely. There are far more microscopic arrangements where energy is spread out than arrangements where it is concentrated. The cooling of the coffee is simply the system moving towards states that have more available configurations, toward higher entropy. This is why entropy is so closely linked to the arrow of time. At the microscopic level, the equations of motion mostly work the same forward and backward. But at the macroscopic level, systems evolve in the direction that increases entropy, because those states dominate the landscape of possibilities. What matters here is that entropy is not about what we know. It is not about missing information in a human sense. It is about the structure of physical reality itself. Even if you knew the exact position and motion of every particle, the statistical weight of different macroscopic states would still exist. This distinction becomes crucial when entropy enters discussions of gravity. When people hear that black holes have entropy, a common misunderstanding appears. They imagine entropy as a measure of ignorance about what fell into the black hole. But that is not what the physics says. The entropy associated with a black hole behaves like a real physical quantity. It obeys laws. It changes in predictable ways. It contributes to thermodynamic balances. This means the entropy is not just in our description, it is in the system. That realization forced physicists to ask a difficult question. If a black hole has entropy, what microscopic configurations are being counted? What are the degrees of freedom responsible for that enormous number? For ordinary matter, the answer is clear: atoms, molecules, particles. But for space-time itself, the answer is not known. What is known is how the entropy scales. For a black hole, entropy grows with the area of the event horizon. Double the radius, and the area increases dramatically. The entropy follows that area, not the volume inside. This scaling is not optional. It comes out of combining well-established pieces of physics. If you try to change it, you break the consistency of the theory. Once this fact is accepted, a boundary appears. There is a maximum amount of entropy that can fit into a given region of space without forming a black hole. That maximum depends on the surface surrounding the region. This is a profound constraint. It says that nature itself enforces a limit on how much information can be packed into space, not based on how much room there is inside, but based on the size of the boundary. At first, this limit seems relevant only for extreme situations: collapsing stars, high-energy experiments, early universe conditions. But limits have a way of shaping theories even when they are not actively reached. In thermodynamics, the existence of entropy limits determines which processes are possible and which are not. In gravity, an entropy bound suggests that space-time may have a finite capacity for information, even in regions that appear empty. This brings us back to the original puzzle of gravity's uniqueness. If space-time itself carries entropy, then space-time may have microscopic degrees of freedom. And if space-time has microscopic degrees of freedom, then its large-scale behavior could be emergent, not fundamental. This does not mean space-time is made of particles in the usual sense. It means that the smooth geometry described by general relativity might be an effective description, averaging over deeper structures we do not yet see directly. The idea is unsettling because it challenges something deeply ingrained. We are used to thinking of space as the container for everything else. But entropy suggests that space itself might be part of the system, subject to statistical laws. At this stage, no claims are being made about what those microscopic degrees of freedom are. No model is being assumed. The only thing being followed is the logic of entropy and the constraints imposed by gravity. And that logic keeps pointing toward boundaries. If information is limited by area, then surfaces matter in a way volume does not. Horizons become more than geometric features. They become bookkeeping, devices for information. This insight sets the stage for the next step, where the idea of boundaries encoding bulk physics is taken seriously and pushed to its limits. The moment boundaries enter the conversation, the role of space quietly changes. Space stops being just a passive container and starts behaving like something with structure, rules, and limits. That shift is subtle, but it carries enormous consequences. In ordinary physics, boundaries are often conveniences. We draw a box around a system so we can analyze it. The boundary helps us define what is inside and what is outside, but it does not usually carry deep physical meaning on its own. The important action happens in the volume. Gravity challenges that assumption. When a boundary becomes a horizon, it is no longer optional. An event horizon is not something we draw for convenience. It is a physical feature of space-time. It marks a point of no return. Information that crosses it cannot be recovered by observers outside. And yet, the laws of physics insist that information is not simply destroyed. This tension between information conservation and horizons is what makes gravitational entropy so unsettling. The entropy associated with a black hole is not hidden somewhere inside. It is tied directly to the horizon itself. The surface carries the bookkeeping. Once this idea is accepted, a natural question follows. If horizons carry entropy because they hide information, then could entropy be associated with other kinds of boundaries as well? Could the very act of separating regions of space-time create thermodynamic properties? This question leads away from black holes and towards space-time more generally. Imagine an observer accelerating through empty space. According to quantum field theory, that observer does not see emptiness. They see a warm bath of particles, a kind of horizon induced by their acceleration. Temperature appears, not because the space is filled with matter, but because of the observer's relationship to space-time itself. Here again, entropy and temperature appear without traditional matter playing the central role. They arise from geometry and information access. These examples suggest that entropy is not limited to substances or particles. It can be associated with space-time structure, with horizons, with what can and cannot be observed. Entropy becomes a measure of lost access, of hidden degrees of freedom. This perspective makes a certain kind of idea feel less radical than it once did. If entropy and temperature can emerge from space-time geometry, then perhaps forces can too. In everyday physics, entropic forces are well understood. A stretched polymer returns to its relaxed state, not because of a fundamental pull, but because there are more microscopic configurations available when it is relaxed. The force emerges from statistics, not from a basic interaction. The question that now quietly forms is whether gravity could behave in a similar way. This question does not claim gravity is an entropic force. It asks whether some aspects of gravity might emerge from entropy gradients, from systems naturally moving towards states with more available microscopic configurations. The idea is delicate. Gravity is not like a rubber band. It shapes space-time itself. Any analogy must be handled carefully, and many proposed models fail under close inspection. But the reason the question is taken seriously is not analogy. It is consistency. Entropy appears wherever gravity becomes extreme. Information limits appear wherever space-time is pushed to its edge. Horizons behave like thermodynamic objects. These are not coincidences, they are clues. At the same time, caution is essential. No experiment has shown that gravity is fundamentally entropic. General relativity remains accurate and indispensable. Any deeper explanation must reproduce its predictions exactly where they have been tested. What entropy offers at this stage is not an answer, but a framework. It suggests that gravity may be less like a fundamental push and more like a collective effect, arising from deeper rules about information and accessibility. Whether that suggestion survives further scrutiny is an open question. What matters for now is that the logic leading to it is not speculative storytelling. It is driven by established physics confronting its own limits. As the pieces come together, a pattern begins to emerge. Gravity, entropy, and information seem to orbit the same central mystery. A mystery not about forces alone, but about how space-time itself is organized. To move forward, physicists needed a principle that could turn this pattern into something precise. A way to say, in clear mathematical terms, how boundaries, information, and geometry are related. That principle did not come from experiment. It came from following the implications of black hole entropy to their logical conclusion. For a long time, black holes were treated as mathematical curiosities. They appeared as strange solutions to Einstein's equations, places where gravity became so strong that the equations themselves seemed to break. Many physicists assumed they were not real, or if they were real, they would never matter outside of extreme thought experiments. That assumption did not survive contact with reality. Black holes form naturally when massive stars exhaust their fuel and collapse under their own gravity. Observations across the electromagnetic spectrum now show strong evidence that black holes exist throughout the universe. Some are only a few times more massive than the Sun. Others sit at the centers of galaxies, weighing millions or even billions of times more than the Sun. These objects are not rare, they are part of the cosmic landscape. At first glance, black holes appear deceptively simple. According to general relativity, once a black hole settles down, it can be completely described by just a few quantities. Its mass, its rotation, its electric charge, everything else about the matter that formed it seems to disappear behind the event horizon. This simplicity earned black holes a nickname. They were said to have no hair, no detailed features, no memory of their past beyond a small set of numbers. That idea created a paradox long before anyone talked about entropy. If black holes erase almost all information about what falls into them, then they seem to violate one of the most basic principles of physics. In quantum mechanics, information is not supposed to be destroyed. The exact state of a system may become difficult to reconstruct, but it is not erased from reality. At first, this tension was easy to ignore. Black holes were thought to be completely black. Nothing escaped them. No radiation, no signal. If information disappeared behind the horizon, there was no obvious way to test what happened to it. Then, in the 1970s, that picture changed in a way no one expected. When physicists studied quantum fields near a black hole horizon, they discovered something remarkable. Black holes are not truly black. They emit radiation, slowly, steadily, as if they have a temperature. This radiation is not coming from inside the black hole. It arises from quantum effects near the horizon itself. To a distant observer, the black hole behaves like a warm object, losing energy over time. This was a shock. Temperature had entered a place where it did not seem to belong. Once temperature appeared, entropy followed. Thermodynamics demanded it. If a black hole has a temperature, then it must have entropy. And that entropy turned out to be enormous. The entropy of a black hole is not proportional to how much stuff fell in. It is proportional to the area of the event horizon. The larger the horizon, the greater the entropy. This relationship is precise, not approximate. It contains fundamental constants and links gravity, quantum theory, and thermodynamics in a single expression. This result was not speculative. It came from careful calculations using well-established physics, quantum field theory in curved space-time, general relativity, statistical reasoning. What made it revolutionary was not just that black holes have entropy, it was how that entropy scales. In ordinary systems, entropy grows with volume. More space means more room for microscopic states. Black holes refuse to follow that rule. Their entropy grows with surface area instead. This single fact overturned decades of intuition. It suggested that the maximum amount of information that can exist inside a region of space is not determined by how much volume there is, but by how much boundary surrounds it. Push too much information into a region, and gravity responds by forming a horizon. Beyond that point, no additional information can be accessed from the outside. Black holes, once thought of as exotic oddities, suddenly became guides. They showed what happens when gravity, quantum mechanics, and entropy are forced to coexist. The lesson was not that black holes are strange. The lesson was that space-time itself might be hiding something fundamental. If space-time can carry entropy, then it must have microscopic degrees of freedom. And if those degrees of freedom exist, then the smooth geometry described by general relativity cannot be the full story. It must be an effective description, emerging when many underlying possibilities are averaged together. This realization did not solve the problem of gravity, it sharpened it. Black holes revealed that gravity is not just about motion and curvature, it is about information, about limits, about what can be known and what must remain hidden. Once that door was opened, it could not be closed. Once black holes were understood as thermodynamic objects, a deeper tension came into focus. Thermodynamics is built on conservation laws. Energy is conserved. Entropy behaves predictably. Processes follow statistical rules that do not allow information to simply vanish. But black holes seem to sit at the edge of those rules. If a black hole has entropy, then that entropy must be counting something real. It must correspond to microscopic configurations, just like the entropy of a gas counts molecular arrangements. But what are the microscopic states of a black hole? Where are they located? And how do they preserve information if everything that falls in appears to be lost behind the horizon? At first, there were no clear answers. General relativity does not describe microscopic structure. It treats space-time as smooth and continuous. Quantum field theory describes particles and fields, but it assumes space-time as a fixed background. Neither framework alone could explain where black hole entropy comes from. Yet the entropy formula itself was unambiguous. It said that the number of microscopic states grows exponentially with the area of the horizon, not the volume, the surface. This was not a small correction. It was a fundamental departure from how physics had always counted degrees of freedom. To understand how radical this is, consider an ordinary object like a star. Its entropy depends on how many particles it contains and how they are arranged. If you compress the star, its volume shrinks, but its entropy remains tied to the number of particles inside. There is no special role for the surface. A black hole behaves differently. Once a horizon forms, the interior volume can grow or shrink depending on how you define it, but the entropy remains tied to the area of the horizon. The bookkeeping happens at the boundary. This suggests that the horizon is not just a geometric surface. It is a physical object in its own right, carrying information. That idea immediately raises another problem. If black hole entropy counts microscopic states, and those states live on or near the horizon, then information about what fell into the black hole is not destroyed. It is somehow encoded there. But encoded how? This question became known as the black hole information problem. It is not a philosophical puzzle. It is a precise conflict between quantum mechanics and classical gravity. Quantum mechanics insists that information is conserved. Classical gravity, when taken at face value, seems to erase it. For decades, physicists debated whether quantum mechanics might fail in extreme gravitational situations. Some proposed that information really is lost in black holes. Others argued that quantum theory must survive intact, and that our understanding of spacetime must change instead. Over time, the balance shifted. The deeper physicists studied the problem, the more it appeared that giving up information conservation would break quantum mechanics in unacceptable ways. The alternative was to accept that spacetime, as described by general relativity, is incomplete. This did not mean general relativity is wrong. It means it is like thermodynamics, a powerful, accurate theory that works at large scales but does not reveal the microscopic details underneath. Just as thermodynamics does not tell you about atoms directly, general relativity may not tell you about the fundamental constituents of spacetime. Black holes forced this comparison into the open. They behaved like thermodynamic systems, complete with temperature and entropy, yet they were described by a geometric theory that had no place for microscopic degrees of freedom. The only way to reconcile these facts was to accept that spacetime itself must have an underlying structure, even if we do not yet know what it is. This realization changed how physicists approached gravity. Instead of trying only to quantize the geometry directly, some began to look for clues in information theory. They asked how information could be stored, processed, and limited in gravitational systems. The entropy bound provided a guiding principle. It suggested that nature enforces a maximum information density, and that this density is controlled by area rather than volume. This principle did not solve the information problem on its own, but it pointed toward a new way of thinking, one where geometry, entropy, and information are not separate concepts, but different expressions of the same underlying reality. As these ideas developed, a bold proposal began to take shape. If information lives on boundaries, and if gravity responds to information limits, then perhaps the physics inside a region of space can be fully described by data on its surface. At first, this sounded like an abstract curiosity, but soon it would become one of the most precise and influential ideas in modern theoretical physics. The idea that the physics inside a region might be encoded on its boundary was not introduced as a metaphor. It was a practical response to a growing pile of contradictions. Black holes had made it clear that information, gravity, and geometry could not be treated as separate subjects anymore. They were entangled in a way that could not be undone. If information is conserved, and if black holes do not destroy it, then that information must remain accessible in some form. But classical spacetime offers no obvious place to store it. The interior is hidden. The exterior sees only mass, rotation, and charge. The horizon becomes the only remaining candidate. This shifts the role of the horizon dramatically. It stops being just a one-way membrane and starts looking like a physical system with its own degrees of freedom. Not particles in the usual sense, but something capable of encoding vast amounts of information. What is striking is that this conclusion does not depend on exotic assumptions. It follows from insisting that well-tested principles continue to hold. Quantum mechanics demands information conservation. Thermodynamics demands consistent entropy accounting. General relativity describes horizons as unavoidable features of strong gravity. All three point toward the same uncomfortable place. Space-time, as we usually think about it, may not be fundamental. This does not mean space-time is an illusion. It means it may be emergent. A large-scale description that hides a deeper layer, just as fluid dynamics hides atomic motion. At everyday scales, the smooth picture works perfectly. But when pushed to extremes, the underlying structure begins to show through. Black holes are not special because they are exotic. They are special because they expose the limits of our descriptions. They are places where space-time is stretched to its breaking point and where information accounting cannot be ignored. Once physicists accepted this, a new way of organizing theories became possible. Instead of building physics from the inside out, starting with fields filling space, they began to ask whether space itself could be reconstructed from more abstract data, from correlations, from entanglement, from information shared across boundaries. This was not an abandonment of geometry. It was a deeper attempt to explain it. In this view, geometry becomes secondary. Distance, curvature, and even dimensionality may arise from how information is structured. Two regions of space feel close, not because they are adjacent in some pre-existing grid, but because they share strong informational connections. These ideas were initially speculative. They needed a concrete mathematical setting to be taken seriously, a place where they could be tested for internal consistency, even if experiments were not yet possible. That setting would come from an unexpected direction. String theory, originally developed as a possible theory of particles, had grown into a framework that naturally included gravity. Within that framework, physicists discovered a remarkable correspondence, a precise mathematical relationship between a gravitational theory in a higher dimensional space and a non-gravitational theory defined on its boundary. This was not just an analogy, it was an exact equivalence within a specific class of spacetimes. Calculations done in one description could be translated into the other, and the answers matched. For the first time, the idea that spacetime physics could be encoded on a boundary was not just a principle, it was a working model. This correspondence did not describe our universe. It applied to idealized spaces with special symmetries. But it demonstrated something profound. Space-time geometry could emerge from a theory with no gravity at all. That result changed the conversation. The holographic idea was no longer just a constraint suggested by black holes. It became a concrete tool, a way to study quantum gravity indirectly by translating it into a different language. And once that door was opened, the question of whether gravity itself could emerge from more fundamental principles stopped sounding radical. It started sounding inevitable. The next step is to understand that correspondence carefully, not as a claim about reality, but as a proof of concept, a demonstration that space-time, gravity, and geometry can arise from something deeper under the right conditions. That is where the story moves next. By the time the holographic idea took shape, it did not feel like a sudden leap. It felt like a conclusion that had been quietly forming for years. Black holes had forced physicists to accept that information behaves differently in the presence of gravity. Horizons had revealed that boundaries matter more than volume, and quantum mechanics had refused to surrender its rules. The holographic principle emerged as an attempt to hold all of these facts together without contradiction. At its core, the principle makes a very restrained claim. It says there is a limit to how much information can exist within a region of space, and that limit is proportional to the area of the boundary surrounding that region. Not because the interior is empty, and not because reality is an illusion, but because gravity enforces a maximum information density. This idea runs directly against everyday intuition. We experience space as something that can be filled. A bigger container holds more objects. A larger room holds more air. Volume feels like the natural measure of capacity, but gravity changes the rules. If you try to pack too much energy or information into a region, space-time responds. The region collapses into a black hole. Once that happens, the amount of information that can be accessed from the outside is determined by the area of the horizon. Any additional information is hidden behind it. This means the boundary is not just a geometric surface. It represents a limit, a fundamental constraint imposed by nature itself. The holographic principle does not say that everything inside a region is literally painted on its surface. That image is misleading. What it says is that any consistent physical description of the interior cannot contain more information than the boundary allows. In this sense, holography is not a picture of reality. It is a bookkeeping rule. This distinction matters. The principle does not replace space-time. It constrains it. It does not tell you what the microscopic degrees of freedom are. It tells you how many of them there can be. What makes this powerful is how conservative the logic is. No new particles are assumed. No speculative forces are introduced. The argument comes from demanding consistency between general relativity, quantum mechanics, and thermodynamics. If those theories are all approximately correct in their domains, then something like a holographic bound seems unavoidable. At first, the principle was abstract. It did not provide a way to calculate anything concrete. It was more like a warning sign, telling theorists that certain ways of thinking about space-time could not be right. But warnings can be productive. Once physicists accepted that information is limited by area, they began looking for theories where this limit is naturally built in. They asked whether there exist systems where the physics of a volume can be fully captured by degrees of freedom living on a lower dimensional boundary. That question would soon receive an unexpected and precise answer. Before that happens, it is important to understand what the holographic principle does not claim. It does not say that space is fake. It does not say that reality is a projection. It does not say that dimensions are illusions. Those interpretations go far beyond the physics. What holography suggests is much more restrained. It suggests that our usual way of counting degrees of freedom overcounts. It suggests that the smooth volume of space may contain redundancies, descriptions that do not correspond to independent physical information. In other words, space-time might be an efficient description, but not the most fundamental one. This idea is unsettling because it challenges a deeply rooted assumption. That space is the arena in which physics happens, rather than something that emerges from it. The holographic principle invites us to reverse that perspective, to treat geometry as a consequence, not a starting point. At this stage, the principle is still just that, a principle. It tells us what must be true if our theories are to remain consistent. It does not yet tell us how reality actually implements these limits. To move forward, physicists needed more than a constraint. They needed an example, a concrete model where holography is not just an idea, but a working mathematical correspondence. That example would arrive in a surprising place, through a theory that was not originally designed to explain space-time at all. Once the idea of a holographic limit was taken seriously, it began to influence how physicists judged their own theories. Models that allowed unlimited information density started to look suspicious. Descriptions that treated every point in space as an independent degree of freedom began to feel excessive. This was not because those models failed immediately, but because they conflicted with what gravity seemed to demand. If space-time really enforces an upper bound on information, then any fundamental theory must respect that bound from the beginning. It cannot be something added later as a correction. It has to be built into the structure of the theory itself. This realization pushed researchers to look for frameworks where gravity and quantum mechanics are not stitched together awkwardly, but emerge from a common foundation, a place where holography appears naturally, not as an afterthought. One such framework already existed, though it had not been created with this goal in mind. String theory began as an attempt to describe particles as tiny, vibrating strings rather than point-like objects. Over time, it evolved into a much broader mathematical structure. One of its unexpected features was that gravity appeared automatically. The theory did not need gravity to be added by hand. It was already there. Within this framework, physicists studied spacetimes with special symmetries. These spaces were not chosen because they looked like our universe. They were chosen because they were mathematically tractable, highly idealized, carefully controlled. In these settings, something remarkable happened. Physicists discovered that a gravitational theory defined in a higher dimensional space could be exactly equivalent to a quantum theory, with no gravity defined on its boundary. Every physical quantity in the gravitational description had a counterpart in the boundary theory. Energies matched, correlations matched. Even complex dynamical processes could be translated from one side to the other. This was not an approximation. It was an exact correspondence within that mathematical setting. For the first time, holography was not just a principle limiting information. It was a working duality, a dictionary between two very different descriptions of reality. What made this discovery so powerful was not that it described the real universe. It does not. The space-time involved has properties our universe does not appear to have, but the correspondence proved something important. It showed that space-time geometry can emerge from a theory that does not contain gravity at all. That curvature, distance, and even dimensionality can arise from more abstract relationships in a lower dimensional system. This was a shock to intuition, but it was also a relief. It meant that the strange hints coming from black hole entropy were not leading into a dead end. There was at least one consistent mathematical world where all those hints came together cleanly. In that world, the holographic limit is not mysterious, it is automatic. The boundary theory simply does not have enough degrees of freedom to violate it. This shifted the way physicists thought about space-time. Instead of asking how to quantize geometry directly, they began to ask how geometry might be reconstructed from more basic data, from correlations between quantum degrees of freedom, from patterns of entanglement. The boundary theory did not look like space at all. It was a collection of quantum fields interacting with each other. And yet, when viewed in the right way, those interactions encoded a smooth, higher dimensional space-time. This suggested a new possibility. That space is not fundamental, but relational. That distance emerges from how strongly different parts of a system are connected, not from a pre-existing grid. These ideas were still theoretical. They relied on special symmetries and idealized conditions. No experiment could test them directly, but they changed the standard of proof. It was no longer enough to say that gravity might be emergent. There was now an explicit example where something like gravity does emerge, mathematically and consistently, from a non-gravitational system. That example did not answer every question, but it showed that the idea was coherent. The next step is to understand that correspondence in more detail, to see exactly how geometry arises and what role information and entropy play in that emergence. Only then can we return to the original question with clarity. Not whether gravity feels like an entropic force, but whether gravity could, in principle, arise from the statistical behavior of deeper degrees of freedom. As this correspondence was explored more deeply, its most unsettling feature became clearer. The boundary theory did not contain space in the way we usually imagine it. There were no distances in the bulk sense, no directions pointing inward, no obvious notion of gravity pulling things together. And yet, when physicists translated the mathematics carefully, a higher dimensional space-time appeared. It was not added by hand. It emerged. What determined how far apart 2 points were in the emergent space was not a ruler or a coordinate grid. It was the pattern of relationships in the boundary theory, how strongly different parts of the system were correlated, how much information they shared, how entangled they were. This was a profound shift. It suggested that geometry could be built from information. That space might be a secondary concept, arising from the way quantum systems organize their correlations. In this picture, distance becomes a measure of connection. Regions that share a lot of information behave as if they are close. Regions that share very little behave as if they are far apart. Geometry reflects entanglement structure. This idea did not come from poetic language. It came from calculations. When physicists adjusted patterns of entanglement in the boundary theory, the shape of the emergent spacetime changed in precise ways. Remove entanglement, and space began to fall apart. Increase it, and geometry became smoother and more connected. This provided a new lens through which to view gravity. If spacetime geometry can emerge from information relationships, then gravitational dynamics may also have an informational origin. Curvature might reflect how information is distributed. Gravitational attraction might reflect how systems reorganize themselves toward states with greater informational consistency. This does not mean gravity is simply an entropic force in the everyday sense. The correspondence is far more subtle. But it does suggest that gravity and entropy may be two expressions of the same underlying principles. At the same time, the limits of the correspondence remained clear. It worked in special spacetimes with specific symmetries. It relied on mathematical idealizations far removed from the universe we observe. No one claimed it was a literal model of reality. Its importance lay elsewhere. It showed that ideas once considered philosophical could be made precise, that questions about the emergence of space and gravity could be translated into equations. That information was not just a bookkeeping tool, but a structural element of physical law. This raised an important caution as well. Not every emergent description applies universally. Thermodynamics emerges from atoms, but it does not replace atomic physics. Hydrodynamics emerges from molecular motion, but it fails at very small scales. Similarly, if gravity emerges from deeper informational rules, general relativity would still remain valid where it has been tested. Any deeper theory would have to reproduce its predictions exactly in those regimes. The holographic correspondence did not overthrow gravity. It respected it. It explained how it could arise without contradicting what is already known. This distinction matters because it keeps speculation anchored to evidence. The correspondence does not say the universe is a hologram. It says that holography is possible, that nature allows at least one consistent way for spacetime and gravity to emerge from non-gravitational degrees of freedom. With that possibility established, physicists could ask a new kind of question. Not whether gravity is fundamental by assumption, but whether it must be fundamental. If gravity can emerge in one consistent framework, could it emerge more generally? Could gravitational behavior arise from entropy gradients, from information flow, from systems naturally evolving towards states with more available configurations? This question marks a turning point. It shifts the focus away from geometry alone and toward dynamics, away from static limits and toward forces. To explore that idea, physicists turn to a concept that already existed in statistical physics, a concept that produces real forces without invoking fundamental interactions. Entropic forces. That is where the next chapter takes us. When physicists talk about forces, the picture is usually straightforward. Something pushes, something pulls. A field exists, and objects respond to it. Electricity pulls charges together. Magnetism aligns materials. Gravity curves paths through spacetime. Each force feels fundamental, built into the structure of nature itself. But there is another kind of force that does not come from a basic interaction at all. It comes from statistics. Entropic forces appear not because something is pulling directly, but because systems naturally evolve towards states that have more microscopic possibilities. The force is not written into the laws at the smallest scale. It emerges when many degrees of freedom act together. This idea is not exotic. It is taught in standard physics courses. It shows up in polymers, gases, and soft matter systems. It is measurable, predictable, real. A simple example helps make this concrete. Imagine a long chain made of many linked segments floating in a warm environment. Each segment jiggles randomly due to thermal motion. When the chain is relaxed, it can bend and curl in countless ways. When you stretch the chain, you restrict its possible configurations. There are fewer ways for it to exist while stretched. As a result, the chain naturally tends to return to its relaxed state. Not because there is a fundamental force pulling it inward, but because there are vastly more microscopic arrangements available in that state. The restoring force arises from entropy. If you pull on the chain, you feel resistance. That resistance is an entropic force. Nothing in this system violates fundamental physics. No new interaction is introduced. The force emerges from probability and statistics. This idea changes how forces can be understood. It shows that not every force needs to be fundamental. Some forces reflect collective behavior, not basic interactions. Once this is understood, a natural question forms. If entropic forces exist in ordinary systems, could something like gravity arise the same way? This question did not come from analogy alone. It came from patterns that had already been observed. Gravity appears alongside entropy in black holes. Space-time geometry seems tied to information limits. Boundaries behave like thermodynamic objects. Geometry emerges from entanglement in holographic models. Seen together, these facts invite a careful speculation. Not a claim, but a question. Could gravity be an emergent phenomenon? Could it arise from the statistical behavior of microscopic degrees of freedom, rather than being a fundamental interaction like electromagnetism? This idea does not replace general relativity. It does not deny its accuracy. Any emergent description would have to reproduce Einstein's equations in the regimes where they have been tested. That requirement is non-negotiable. The proposal is more subtle. It suggests that the equations of gravity might play a role similar to the laws of thermodynamics. Powerful, universal, accurate at large scales, but not revealing the microscopic details underneath. This perspective reframes the search for quantum gravity. Instead of asking how to quantize space-time directly, it asks what microscopic rules could give rise to space-time and gravity as effective descriptions. One of the most widely discussed versions of this idea was proposed by Eric Verlinde. He suggested that gravity might arise as an entropic force associated with changes in information related to the positions of matter. The proposal was bold, but it was also cautious. It did not claim to be complete. It did not claim experimental confirmation. It offered a framework to explore whether gravitational dynamics could be derived from statistical principles. In this picture, gravity is not mediated by particles pulling on each other. It is a response of an underlying information system as matter rearranges itself. Objects move in ways that increase the total number of available microscopic configurations. This idea immediately attracted attention and criticism. Some aspects reproduced familiar gravitational behavior. Others struggled when confronted with detailed observations. The proposal sparked debate precisely because it touched a deep nerve. It challenged assumptions that had gone unquestioned for decades. What matters for our story is not whether the proposal is correct. It is why it was taken seriously at all. Entropic forces are real. Entropy plays a central role in gravitational systems. Space-time appears to obey information limits, and holographic models show that geometry can emerge from non-geometric data. Given all of that, asking whether gravity could be emergent is not reckless. It is a reasonable response to the evidence. But reasonable questions still need answers. And those answers must come from observation. That is where the discussion becomes more difficult. Because gravity is measured not in laboratories, but across galaxies. And any proposal that modifies gravity must confront the full weight of astronomical data. That confrontation is where the idea of emergent gravity faces its hardest tests. Once the idea of gravity as an entropic force was placed on the table, it faced an immediate and unavoidable challenge. Gravity is not something we infer indirectly in small systems. It shapes the structure of the entire universe. Any proposal that reinterprets gravity must explain why galaxies rotate the way they do, why light bends around massive objects, and why the large-scale structure of the cosmos looks the way it does. These are not optional details. They are the strongest evidence we have for how gravity behaves. In the standard picture, Much of this evidence points toward the existence of dark matter. Galaxies rotate too fast for the visible matter they contain. Clusters of galaxies bend light more strongly than expected. The cosmic web forms patterns that match simulations only when additional unseen matter is included. Dark matter is not observed directly, but its gravitational influence is consistent across many independent measurements. Any alternative explanation must reproduce all of these successes, not just a subset. Emergent gravity proposals attempt to do this by modifying how gravity behaves at very large distances or very low accelerations. In some cases, these models can reproduce the flat rotation curves of galaxies without invoking dark matter. This is often presented as a success, but matching one class of observations is not enough. When these models are applied to gravitational lensing, the bending of light by massive structures, difficulties arise. The predicted lensing effects often fall short of what is observed. Similarly, when applied to the growth of cosmic structure over time, emergent gravity models struggle to reproduce the observed distribution of galaxies and clusters. These shortcomings do not mean the ideas are wrong. They mean they are incomplete. Physics does not advance by abandoning theories at the first sign of difficulty, but it also does not accept ideas that work only where they are convenient. Gravity is tested across many scales, from laboratory experiments to the largest structures in the universe. So far, general relativity combined with dark matter passes these tests remarkably well. This places emergent gravity proposals in a very specific position. They are not replacements for existing theories. They are exploratory frameworks. Attempts to see whether the deep connections between gravity, entropy, and information can be extended beyond black holes and idealized models. That distinction matters. There is a difference between saying gravity could be emergent in principle and saying current emergent gravity models describe reality. The first is a theoretical possibility. The second requires evidence that does not yet exist. At the same time, the difficulties faced by these proposals have taught physicists something valuable. They have clarified which features of gravity are tightly constrained by observation, and which might still allow deeper explanations. They have also reinforced an important lesson. Gravity is not just a force between objects. It shapes space-time itself. Any attempt to explain gravity as emergent must account for that geometric aspect, not just reproduce force laws. This realization has shifted attention away from simple analogies and toward more subtle questions. Questions about how space-time geometry could arise from information, how curvature could reflect patterns of entanglement, how gravitational dynamics could be encoded in statistical behavior without losing geometric meaning. These questions are not answered by current entropic gravity models, but they are informed by them. In this sense, emergent gravity proposals have served as probes. They have tested the idea that gravity might not be fundamental, and in doing so, they have revealed just how tightly gravity is woven into the fabric of space-time. What remains is a careful balance. On one hand, black hole physics and holography suggest that space-time and gravity may emerge from deeper principles. On the other hand, observational evidence demands that any such emergence reproduces general relativity with extraordinary precision. Holding both of these facts at once is not easy, but it is necessary. To move forward, physicists began to focus less on modifying gravity directly and more on understanding the relationship between geometry and information at a fundamental level. Instead of asking how gravity changes, they asked how space itself might arise. That shift leads away from force laws and toward quantum information, toward entanglement, toward the idea that space-time geometry may be encoded in patterns of quantum correlations. This is where the discussion naturally turns next. The move toward quantum information was not a change of subject, it was a change of perspective. Instead of treating information as something carried by matter moving through space, physicists began to ask whether information might be what gives space its structure in the first place. Quantum mechanics had already shown that information behaves in ways that have no classical counterpart. Entanglement links distant systems so that they cannot be described independently, even when separated by large distances. These correlations are not signals. They do not transmit energy or matter, but they are real, measurable, and unavoidable. For a long time, entanglement was treated as a curiosity, a strange feature of quantum theory that challenged intuition but had little to say about gravity. That view changed when holographic models revealed that entanglement patterns on a boundary could determine the geometry of an emergent space. This was a quiet but profound realization. It suggested that the shape of space might reflect how quantum information is shared. In this picture, space-time is not assembled from points. It is assembled from relationships. The more entangled two regions are, the closer they appear in the emergent geometry. Reduce the entanglement and the distance grows. Remove it entirely and space itself begins to fragment. This idea reframes gravity yet again. Instead of being a force acting within space-time, gravity becomes a manifestation of how space-time responds when patterns of information change. Curvature reflects how entanglement is distributed. Dynamics reflect how those distributions evolve. This does not mean gravity is nothing but information. It means information may be more fundamental than geometry. Importantly, this line of thought does not contradict general relativity. In the regimes where general relativity has been tested, the entanglement structure that would give rise to space-time geometry would be extremely stable. The emergent description would look smooth, continuous, and geometric, exactly as observed. The value of this perspective is not that it replaces existing theory, but that it explains why existing theory works so well. It suggests that Einstein's equations may arise as consistency conditions on how information can be arranged, rather than as fundamental laws imposed from the start. At the same time, this approach remains incomplete. It relies on mathematical models that are far removed from experimental access. It works best in highly symmetric situations. It does not yet provide a full description of the universe we observe. But it does something important. It unifies several strands that once seemed unrelated: black hole entropy, holographic limits, entropic forces, quantum entanglement, all begin to look like parts of a single framework. Within that framework, gravity is no longer an isolated mystery. It becomes a consequence of deeper principles governing information and its organization. Whether this picture is ultimately correct remains unknown. Physics has reached this point before, where elegant ideas await experimental guidance. History offers both caution and hope. What is clear is that gravity has forced physics to confront questions it cannot avoid. Questions about the nature of space, about the meaning of information, about what it means for something to be fundamental. These questions do not yield quick answers, but they define the frontier. And as the focus shifts from forces to information, from geometry to entanglement, a new set of puzzles comes into view. Puzzles about what happens to information in extreme situations, about whether information is truly conserved, and about how time itself fits into this emerging picture. That is where the discussion leads next. Ideas about gravity can be elegant. They can be mathematically consistent. They can even solve problems that have resisted explanation for decades. But physics does not decide truth by elegance alone. It decides by confrontation with reality. Gravity is measured not just in equations, but in the motion of stars, the bending of light, and the structure of the universe itself. Any proposal that reinterprets gravity must survive that confrontation. This is where many beautiful ideas begin to strain. The most direct tests of gravity come from astronomy. Galaxies rotate. Light travels across cosmic distances. Clusters of galaxies form and evolve over billions of years. These processes are governed by gravity over enormous scales, far beyond anything that can be reproduced in a laboratory. One of the most persistent puzzles in modern astrophysics is the way galaxies rotate. When astronomers measure how fast stars orbit the centers of galaxies, they find something unexpected. The outer stars move much faster than they should if gravity came only from the visible matter. According to standard gravity, stars farther from the center should move more slowly, just as planets farther from the Sun orbit more slowly. Instead, their speeds remain nearly constant across large distances. This pattern appears again and again across many different galaxies. The conventional explanation is dark matter, an unseen form of matter that does not emit light but contributes gravitationally. When dark matter is included, the observations make sense. The rotation curves match predictions. The same framework explains many other phenomena as well. Emergent gravity proposals attempt to explain these rotation curves without invoking dark matter. In some cases, they succeed at the level of individual galaxies. By modifying how gravity behaves at extremely low accelerations, these models can reproduce the observed flat rotation curves. This result is often highlighted as evidence that something deeper may be at work, but galaxies are only one piece of the picture. Gravity also bends light. This effect, known as gravitational lensing, provides a direct way to map how mass is distributed in space. When light from distant objects passes near massive structures, its path curves. The amount of bending tells us how strong the gravitational field is along the way. Lensing measurements consistently indicate more gravitational influence than visible matter alone can provide. This includes not just galaxies, but clusters of galaxies and large-scale cosmic structures. Here, emergent gravity models face serious challenges. Many struggle to produce enough lensing without adding extra assumptions. Some require additional fields or parameters that reduce their original simplicity. The difficulties grow when these models are applied to the evolution of the universe as a whole. The large-scale structure of the cosmos, the pattern of galaxies and voids, reflects how gravity has shaped matter. Over billions of years, standard models, including dark matter, reproduce these patterns with remarkable accuracy. Emergent gravity proposals have not yet matched this success. This does not mean the ideas are wrong. It means they are incomplete. Physics advances by testing ideas where they are strongest and exposing them where they are weakest. In this case, the weakness lies not in local phenomena, but in global consistency. Gravity must behave correctly everywhere, not just in special regimes. There is another important constraint. General relativity has been tested extremely precisely in environments ranging from planetary motion to gravitational waves. Any modification or reinterpretation of gravity must reduce to general relativity in these regimes, without leaving detectable traces. So far, emergent gravity models have not demonstrated this level of universality. This reality has led many physicists to adopt a cautious stance. The deep connections between gravity, entropy, and information are real and well motivated, but using those connections to replace dark matter or modify gravity directly may be asking too much, too soon. Instead, attention has shifted again. Rather than forcing emergent ideas to explain all observations immediately, researchers have begun treating them as clues. Hints about what a deeper theory of space-time might look like, rather than finished models of the universe. This reframing preserves what is valuable without overstating what is proven. Gravity remains, observationally, exactly as general relativity describes it across an enormous range of scales. Dark matter remains the simplest explanation for many phenomena. At the same time, the theoretical tension between gravity and quantum mechanics remains unresolved. Holding both of these facts together is uncomfortable, but it is honest, and it keeps the door open for progress. Because even if emergent gravity is not the final answer, the ideas that led to it have already changed how physicists think about space, time, and information. They have revealed that geometry and gravity may not be fundamental starting points, but consequences of deeper rules. To explore those rules further, the focus turns once again to quantum information, not as a replacement for gravity, but as a language capable of describing structure where geometry itself may no longer be primary. That shift brings us closer to one of the deepest questions physics can ask: how space is built from something that is not space at all. The challenge of testing these ideas has had an unexpected effect. It has clarified what physics already knows with great confidence and what remains genuinely uncertain. General relativity continues to pass every direct experimental test placed before it. From the precise timing of pulsars, to the motion of planets, to the detection of gravitational waves, its predictions remain accurate within measurement limits. Any deeper explanation of gravity must reproduce all of this behavior exactly where it has been observed. There is no flexibility here. At the same time, the quantum description of nature has proven equally resilient. Quantum mechanics governs atoms, particles, and fields with extraordinary precision. It enforces strict rules about information, probability, and measurement. These rules have been tested in countless experiments, and no consistent violation has ever been observed. The difficulty arises because these two frameworks speak different languages. General relativity describes a smooth spacetime shaped by energy and momentum. Quantum mechanics describes discrete systems governed by probabilities and correlations. Each framework is complete in its own domain, but when they are brought together near black holes or in the earliest moments of the universe, neither is sufficient on its own. This is why ideas about emergence continue to attract attention even when specific models fail observational tests. They offer a way to reconcile these frameworks without discarding their successes. Instead of forcing gravity into a quantum mold designed for other forces, emergence suggests that gravity might be the macroscopic face of a microscopic theory that looks nothing like space-time at all. In such a theory, quantum rules would apply fundamentally, and geometry would arise only as an effective description. This perspective changes how tests are interpreted. Rather than asking whether an emergent gravity model reproduces every astronomical observation today, physicists ask whether the deeper principles suggested by emergence can lead to a theory that does. The failure of early models is not a verdict against the idea, but a guide to what any viable theory must include. One lesson is clear. Any successful framework must explain why spacetime appears smooth and continuous over enormous ranges of scale. It must explain why Einstein's equations emerge so robustly, with the same form everywhere they have been tested. And it must explain how information is preserved even when spacetime develops horizons. These are strict requirements. They rule out many speculative ideas immediately. Another lesson is more subtle. The connection between gravity and entropy does not necessarily imply that gravity itself is an entropic force in the simple sense. It may instead imply that gravitational dynamics are constrained by statistical principles at a deeper level. Principles that limit how information can be distributed and how correlations can evolve. In this view, entropy does not replace gravity, it constrains it. This distinction matters because it avoids a false choice. Physics does not need to decide between gravity as geometry and gravity as entropy. It may be that geometry is the emergent expression of entropic and informational rules, just as pressure is the emergent expression of molecular motion. Seen this way, the failure of current emergent gravity models is not surprising. They are early attempts to connect levels of description that are separated by many layers of complexity. What matters is that the connection exists at all. Black hole thermodynamics, holographic bounds, and quantum entanglement all point toward the same conclusion. Spacetime is not an inert backdrop. It participates in the accounting of information. It obeys limits that resemble thermodynamic laws. And it may arise from microscopic degrees of freedom that do not resemble geometry. This realization reshapes the original question. The question is no longer whether gravity can be derived from entropy in a simple formula. The question is whether gravity emerges from a deeper theory in which entropy and information are fundamental. That is a much harder question, and it cannot be answered by astronomy alone. To make progress, physicists have turned to situations where gravity, quantum mechanics, and information collide most violently. Situations where the usual picture of space-time is pushed to its limits. Those situations involve black holes, horizons, and the fate of information over time. And that brings us to one of the most persistent puzzles in modern physics. What happens to information when gravity becomes so strong that space-time itself seems to tear? That is where the discussion moves next. When gravity becomes extreme, the usual intuitions about space and time begin to fail. Distances lose their meaning. Clocks no longer agree with each other. Surfaces appear where nothing that crosses them can ever return. These are not theoretical curiosities. They are predictions of general relativity, and they describe real situations in the universe. In these environments, information is pushed to its limits. Black holes are the clearest example. Matter falls in. Signals fade away. From the outside, everything seems to freeze at the horizon. Yet quantum mechanics insists that information cannot simply vanish. The state of a system may become scrambled, spread out, or practically impossible to reconstruct, but it is not erased. This tension lies at the heart of one of the deepest problems in physics: the black hole information paradox. If a black hole eventually evaporates through radiation, as quantum field theory predicts, then what happens to the information about everything that fell inside? If the radiation is completely random, information appears to be lost. If the information is somehow encoded in the radiation, then space-time must behave in ways that classical general relativity does not describe. For decades, this paradox resisted resolution. Every proposed answer seemed to break something fundamental. Either quantum mechanics failed, or general relativity failed, or basic notions of causality were violated. What gradually became clear is that the paradox is not a flaw in physics. It is a signpost. It tells us that our description of space-time is incomplete when gravity and quantum effects are both strong. Entropy plays a central role here. The enormous entropy of a black hole suggests that it hides an equally enormous number of microscopic configurations. Those configurations must evolve in a way that preserves information, even if that preservation is not visible in the classical geometry. This is another place where holography and quantum information provide guidance. In holographic models, information is never lost. It is redistributed. What appears hidden in the bulk remains encoded in correlations at the boundary. Time evolution remains unitary, even though the geometric picture looks irreversible. These results do not prove that real black holes behave exactly this way, but they demonstrate that information conservation and horizons can coexist in a consistent framework. This has implications beyond black holes. It suggests that time itself may not be as fundamental as it appears. The arrow of time, so closely tied to entropy increase, may emerge from statistical behavior rather than being built into the deepest laws. In everyday experience, time flows forward. Causes precede effects. Entropy increases. But at the microscopic level, the laws of physics are largely time-symmetric. The preference for one direction emerges when many degrees of freedom act together. If space-time and gravity are emergent, then the flow of time may be emergent as well. Not illusory, not arbitrary, but a large-scale feature arising from deeper rules about information and probability. This possibility remains open. There is no experimental confirmation that time is emergent. There is no complete theory that explains it fully. What exists are hints, connections, partial results that point toward a more unified picture. A picture in which gravity, space-time, entropy, and information are not separate chapters, but different aspects of the same underlying structure. As these ideas continue to develop, they force physics to confront its limits honestly, to distinguish between what is known, what is mathematically consistent, and what remains speculative. Gravity may or may not be emergent. Space-time may or may not arise from information. What can be said with confidence is that the questions themselves are no longer philosophical. They are driven by equations, by consistency, and by evidence. And that changes how we understand not just gravity, but what it means to explain anything at all. Information is easy to overlook because it does not behave like the things we usually call physical. It has no mass. It does not occupy space in the ordinary sense. You cannot hold it in your hand. And yet, modern physics treats information as something that nature keeps careful track of. This idea did not appear overnight. For a long time, information was treated as a human concern, a way for scientists to describe systems rather than something the systems themselves possessed. That view changed with the rise of quantum mechanics. Quantum theory describes physical systems using states. A state is not just a list of properties. It is a complete description of everything that can be known about a system. And according to the rules of quantum mechanics, these states evolve in a very specific way. Their evolution preserves information. This requirement is built into the mathematics. It is called unitarity. If unitarity fails, the entire structure of quantum theory collapses. Predictions stop being reliable. Probabilities no longer add up in a consistent way. As long as gravity is weak, there is no tension. Quantum systems evolve. Information spreads through interactions and entanglement. Nothing fundamental is lost. The conflict appears when gravity becomes strong enough to create horizons. A horizon divides space-time into regions that cannot exchange signals. Once something crosses a horizon, it cannot influence what happens outside. From the perspective of an external observer, information seems to vanish. But quantum mechanics says it cannot. This is the core of the black hole information problem. It is not about curiosity or philosophy. It is a direct clash between two of the most successful frameworks in physics. If black holes exist, and all evidence suggests they do, then they force us to confront this clash head-on. For a time, some physicists considered the possibility that information really is destroyed in black holes. That solution appears simple. It resolves the conflict by sacrificing information conservation. But that sacrifice is too costly. Allowing information loss breaks quantum mechanics in ways that spread far beyond black holes. It leads to inconsistencies that would affect ordinary systems, not just extreme ones. The alternative is to accept that our classical picture of space-time is incomplete. General relativity describes horizons as smooth geometric surfaces with no internal structure. Quantum mechanics suggests that this description is missing something. If horizons carry entropy, then they must correspond to microscopic degrees of freedom. Those degrees of freedom must evolve and store information. From this perspective, information is not destroyed when something falls into a black hole. It is absorbed into degrees of freedom that are not visible in the classical description. This does not mean information remains easy to access. In fact, it becomes extraordinarily difficult to reconstruct. It spreads into correlations that are effectively impossible to track in practice. But loss of access is not the same as loss of information. This distinction is crucial. In quantum information theory, it is common for information about a system to become delocalized. When systems become entangled, the information about their individual states is no longer stored in any single part. It exists in correlations between parts. Black holes appear to operate in a similar way. Information about infalling matter becomes encoded in subtle correlations involving the horizon and the radiation emitted over long periods of time. This picture is supported by theoretical models where information conservation can be demonstrated explicitly. In these models, time evolution remains consistent and reversible at the fundamental level, even though it appears irreversible in the classical geometric description. None of this proves that real black holes behave exactly this way, but it shows that the conflict between gravity and information is not inevitable. It can be resolved without abandoning well-tested principles. Once information is treated as something physical, the role of time also begins to shift. Entropy increases over time. Information spreads. Systems move towards states that are harder to reverse. This is what gives time its apparent direction. At the microscopic level, however, the fundamental laws do not strongly prefer a direction of time. The arrow we experience emerges statistically from the overwhelming likelihood of entropy increasing. If space-time and gravity are emergent, then time itself may be emergent in a similar way, not unreal, but arising from deeper probabilistic rules. This idea remains open. There is no experimental confirmation. There is no complete theory. What exists is a growing recognition that gravity has forced physics to take information seriously in a way it never had to before. And once information is taken seriously, the nature of time can no longer be treated as obvious. When time is viewed through the lens of information, its familiar flow begins to look less fundamental and more like a large-scale effect. In everyday life, time feels relentless. It moves forward. Causes come before effects. Memories point in one direction only. This experience is so consistent that it feels built into the universe itself. Yet the basic equations of physics tell a different story. At the microscopic level, most fundamental laws are almost indifferent to the direction of time. If you take the equations that describe particles and fields and run them backward, they still work. Nothing in those equations marks one direction as special. So where does the arrow of time come from? The answer lies in entropy. Systems begin in states with relatively few microscopic possibilities and evolve towards states with many more. This statistical tendency gives time its direction. It is not imposed by the laws themselves, but by the structure of possible states. This is why broken cups do not spontaneously reassemble, even though the laws of motion allow it. There are far more ways for fragments to be scattered than for them to be perfectly arranged. The forward flow of time reflects the overwhelming dominance of higher entropy states. When gravity enters the picture, this connection becomes even deeper. Gravitational systems have an extraordinary capacity to generate entropy. Black holes, in particular, dominate the entropy budget of the universe. A single black hole can contain more entropy than all the ordinary matter around it combined. This fact has profound implications. If entropy is tied to the arrow of time, and gravity controls the largest contributions to entropy, then gravity plays a central role in shaping time itself, not by dictating its direction directly, but by setting the conditions under which entropy can grow. This perspective suggests that the flow of time we experience may be inseparable from the way space-time organizes. Information. Time may not be a background parameter ticking away independently. It may be a reflection of how information is redistributed as the universe evolves. This idea challenges intuition, but it remains grounded in established physics. It does not require new forces or speculative mechanisms. It follows from combining thermodynamics, quantum mechanics, and gravity, and taking their implications seriously. At the same time, caution is essential. While entropy explains why time has a direction, it does not explain why the universe began in a low entropy state to begin with. That initial condition remains unexplained. Gravity complicates the issue further because gravitational systems behave differently from ordinary thermodynamic systems. For example, when matter clumps under gravity, entropy can increase even as matter becomes more ordered. This counterintuitive behavior is one of the reasons gravity is so difficult to integrate into a simple thermodynamic picture. These subtleties matter when discussing time. If time is emergent, then its emergence depends on specific conditions. It may not behave the same way in all regimes. Near black holes, near the beginning of the universe, or in hypothetical quantum gravity states, the usual notion of time may break down. Some theoretical models suggest that time may not exist as a fundamental parameter at all. Instead, it may arise from correlations between subsystems. Clocks may tick, not because time flows, but because correlations change. This idea is still theoretical. There is no direct evidence that time is emergent in this way. But the fact that it can be modeled consistently is itself significant. It shows that the deep problems raised by gravity do not stop at space. They extend to time. And just as with gravity, the goal is not to replace our everyday experience of time, but to understand why it works as well as it does in the regimes we observe. As the pieces come together, a picture begins to form, one where gravity, Entropy, information, and time are not separate puzzles, but interconnected aspects of a deeper structure. Understanding that structure remains one of the greatest challenges in physics. As these ideas accumulate, it becomes clear that physics is approaching a boundary of its own, not a physical horizon in space, but a conceptual one, a point where familiar explanations stop being sufficient and deeper principles are required. What gravity has revealed is not just a missing equation, but a missing layer of understanding. The equations of general relativity describe how spacetime behaves, but not why spacetime exists in the form it does. Quantum mechanics describes how information evolves, but not how geometry arises from that evolution. Entropy sits between these descriptions. It links microscopic possibilities to macroscopic behavior. It gives time a direction. It limits how much information can be stored. And in gravitational systems, it becomes inseparable from geometry itself. This convergence suggests that gravity may not be a force added to the universe, but a constraint that emerges from how information is organized. Spacetime may not be the stage on which physics happens, but the effective result of deeper rules governing correlations and probabilities. This is a subtle claim. It does not deny the reality of space or time. It does not suggest that gravity is an illusion. It suggests that what feels fundamental may, at a deeper level, be derivative. History offers many examples of such shifts. Temperature was once thought to be a basic property of matter. Pressure felt like a force. Heat seemed like a substance. Each of these turned out to be emergent descriptions of underlying motion. None of that made temperature or pressure less real. It made them better understood. Gravity may be approaching a similar turning point, but physics must remain disciplined. The fact that an idea is elegant does not make it true. The fact that it resolves conceptual tension does not guarantee that nature follows it. What is known with confidence must be kept separate from what is merely plausible. It is known that general relativity describes gravity accurately across an enormous range of scales. It is known that black holes obey thermodynamic laws. It is known that entropy scales with area in gravitational systems. It is known that information conservation is central to quantum mechanics. What is not known is whether spacetime and gravity are fundamentally emergent. What is not known is what the microscopic degrees of freedom of spacetime are. What is not known is how time arises, or whether it arises at all. These unknowns are not failures. They define the frontier. They also explain why physicists speak cautiously about these ideas, not because they lack confidence in established results, but because they understand how easily speculation can outrun evidence. The role of entropy in gravity is not a finished story. It is an active area of research, a set of connections that have been established, and many that remain hypothetical. What can be said is that gravity has forced physics to confront questions it cannot avoid. Questions about limits, information, and the nature of explanation itself. And in confronting those questions, physics has become more honest about what it can claim and what it cannot. That honesty sets the stage for a final assessment, not a conclusion that declares victory, but a careful accounting of where the evidence ends and uncertainty begins. That accounting is where this journey ultimately rests. After following gravity through geometry, entropy, information, and time, it becomes necessary to slow down, not to retreat, but to take stock. Physics advances not only by discovering new ideas, but by carefully separating what is known from what is suggested and what is merely hoped for. This separation matters more here than almost anywhere else. Gravity touches every scale of reality. It governs falling objects and orbiting planets. It shapes stars, galaxies, and the expansion of the universe. Any claim about its nature carries enormous weight. That is why caution is not a weakness in this discussion. It is a requirement. There are things physics knows with extraordinary confidence. General relativity describes gravity as the curvature of spacetime, and it does so with remarkable accuracy. Its predictions have been confirmed by observations of planetary motion, gravitational lensing, time dilation, and gravitational waves. Wherever it has been tested directly, it has worked. Quantum mechanics describes the behavior of matter and energy at small scales with equal precision. Its rules about probability, superposition, and information conservation have been confirmed in countless experiments. No violation of these principles has ever been observed. Thermodynamics, and in particular entropy, provides a bridge between microscopic laws and macroscopic behavior. Entropy explains why time has a direction, why processes are irreversible, and why certain states are overwhelmingly favored over others. These principles are among the most reliable in all of physics. Black holes sit at the intersection of these frameworks. They obey the equations of general relativity. They exhibit thermodynamic behavior. They force quantum mechanics and gravity into direct contact. The discovery that black holes have temperature and entropy is not speculative. It is one of the most solid theoretical results of modern physics. From this foundation, several conclusions follow naturally. Space-time is not an inert background. It responds to energy and momentum. It can form horizons. It can carry entropy. These facts are established. Information is not optional. Quantum mechanics treats it as something that must be preserved. Any consistent theory of nature must account for how information evolves, even in extreme gravitational settings. Entropy plays a central role in gravitational systems. The fact that gravitational entropy scales with area rather than volume is not an assumption. It is a result that has survived decades of scrutiny. From these established results, physics is allowed to ask deeper questions, but it must be careful about how it answers them. It is legitimate to ask whether space-time has microscopic degrees of freedom. It is legitimate to ask whether geometry emerges from deeper principles. It is legitimate to explore whether gravity could arise as an effective description rather than a fundamental interaction. What is not legitimate is to treat these possibilities as settled facts. There is no experimental evidence that space-time is emergent. There is no direct observation of the microscopic structure of space. There is no confirmed theory that derives gravity uniquely from entropy or information alone. Holographic models demonstrate that space-time can emerge in specific, highly idealized settings. They do not demonstrate that our universe works this way. Entropic gravity proposals show that some gravitational phenomena can be reproduced statistically. They do not yet reproduce all known observations. These distinctions are essential. Physics does not progress by declaring that elegant ideas must be true. It progresses by allowing ideas to be tested, constrained, and often discarded. Many beautiful theories have failed this test in the past. The reason ideas about emergent gravity remain active is not because they are proven, but because they address real tensions in existing theory. They offer possible paths forward where direct approaches have stalled. At the same time, the absence of experimental confirmation places firm limits on what can be claimed. Gravity may be emergent, or it may be fundamental in a way we do not yet understand. Space-time may arise from information, or information may require space-time to exist meaningfully at all. At present, physics cannot decide between these possibilities. What it can do is remain honest about the state of knowledge, to recognize which results are solid, which are mathematically consistent but untested, and which remain speculative. This honesty is not a pause in progress. It is progress, because understanding the limits of what we know is what allows new ideas to be pursued without confusion and without mistaking possibility for proof. What physics can claim, then, is not a single answer, but a structured landscape of certainty and uncertainty. At one end of that landscape are results that have survived relentless testing. General relativity is one of them. It describes gravity not as a force in the traditional sense, but as geometry. Objects move the way they do because space-time is curved, and that curvature responds precisely to energy and momentum. This description has been confirmed so many times, in so many independent ways, that it stands as one of the most reliable theories ever constructed. Alongside it stands quantum mechanics, its account of how systems evolve, how probabilities combine, and how information is preserved, has been tested to extraordinary precision. Technologies built on these principles work because the theory works. There is no ambiguity here. Thermodynamics and statistical mechanics occupy a similar position. Entropy is not a philosophical idea. It is a measurable quantity that predicts which processes occur and which do not. Its statistical nature does not weaken it. It strengthens it, because it explains why macroscopic laws are so robust despite microscopic uncertainty. These pillars form the secure foundation. From that foundation, physics is allowed to extrapolate carefully. It is allowed to notice that black holes obey thermodynamic laws. It is allowed to notice that their entropy scales with area. It is allowed to notice that information conservation and space-time geometry come into conflict in extreme situations. These observations are not speculative. They are consequences of applying established theories where they overlap. What comes next is more delicate. Holography shows that, in certain mathematical settings, a gravitational spacetime can be fully described by a non-gravitational theory living on a boundary. This result is mathematically solid within those settings. It is not an analogy, it is a precise correspondence. But those settings are highly special. They involve symmetries and boundary conditions that do not obviously describe the universe we observe. Physics can claim that holography is possible. It cannot claim that the universe is holographic in this sense. Similarly, ideas about emergent gravity show that some aspects of gravitational behavior can arise from statistical principles. They show that forces can emerge without being fundamental. They demonstrate that gravity does not obviously violate such a possibility. What they do not yet show is that gravity in our universe does emerge this way. They do not reproduce all known observations. They do not replace dark matter successfully across all scales. They do not derive general relativity uniquely and completely. This distinction between possibility and proof is where careful reasoning matters most. It is tempting to treat deep conceptual connections as answers. Entropy appears in gravity. Information appears in space-time. Geometry appears in entanglement. These patterns are real and they are meaningful, but patterns alone are not conclusions. Physics advances by closing gaps, not by naming them. At present, the gap between gravity and quantum mechanics remains open. Entropy and information provide strong hints about how that gap might be bridged, but they do not yet provide a bridge that can be crossed experimentally. This does not diminish their importance. It clarifies it. Entropy has already changed how gravity is understood, even without resolving quantum gravity. It has revealed limits on information. It has exposed hidden structure in space-time. It has forced physicists to rethink what counts as a fundamental degree of freedom. Information theory has done the same. It has provided tools to talk about correlations where geometry breaks down. It has reframed old paradoxes in ways that allow progress without contradiction. What physics can claim then is that gravity is deeply entangled with entropy and information. Not metaphorically, but structurally. Any future theory of quantum gravity will almost certainly treat these concepts as central, not peripheral. What physics cannot yet claim is that gravity is nothing but entropy, or that space-time is nothing but information. Those statements go beyond the evidence. Holding this line is not a failure of imagination. It is a discipline earned through experience. The history of physics is filled with ideas that were compelling, elegant, and wrong. It is also filled with ideas that began as vague hints and later became central pillars. The difference was not enthusiasm, it was evidence. Recognizing where we stand now is part of that process. At this point, the most honest position physics can take is neither confident conclusion nor cautious retreat. It is careful balance. Gravity might be emergent, space-time might arise from information, time itself might be a large-scale consequence of statistical behavior. None of these ideas violate known laws. Many are supported by deep mathematical consistency. Some are even required to resolve long-standing paradoxes. but none are confirmed by experiment. That boundary matters. Physics has learned, sometimes painfully, that nature does not always follow the most elegant path available to human reasoning. Concepts that feel inevitable can turn out to be approximations. Concepts that feel artificial can turn out to be fundamental. What keeps progress grounded is the willingness to separate what works from what inspires. What works is clear. General relativity works. Quantum mechanics works. Thermodynamics works. Black hole entropy works as a theoretical result that unites these frameworks in a precise way. What inspires is the realization that these frameworks touch each other in ways that seem too structured to be accidental. Entropy appearing in gravity, information limits shaping space-time, geometry emerging from entanglement. These are not random coincidences. They are signposts. Signposts do not tell you where you are going. They tell you where to look. The danger lies in mistaking signposts for destinations, in treating suggestive ideas as settled truths, in allowing language to outrun evidence. The reason careful phrasing matters so much in this subject is that the concepts themselves are subtle. Words like emergent, holographic, and informational carry intuitive meanings that can mislead. In physics, they refer to specific mathematical and conceptual structures, not metaphors. This is why conservative claims are not a limitation. They are a strength. They allow ideas to develop without becoming dogma. They allow multiple approaches to coexist without forcing premature conclusions. They allow evidence, when it arrives, to speak clearly. The story of gravity and entropy is not a story with a clean ending. It is a story about how physics responds when its most successful theories meet their limits. It is about what happens when geometry stops being enough and information refuses to be ignored. In that sense, the question is no longer whether space-time is emergent or fundamental. The question is how far the existing clues can be pushed before new principles are required. That question remains open, and it is precisely because it remains open that it continues to drive some of the deepest research in modern physics, not with promises, but with restraint, not with certainty, but with clarity. After tracing gravity through entropy, information, and time, what remains is not a finished picture, but a set of open questions that refuse to disappear. These questions are not gaps left by carelessness. They are gaps left by honesty. Physics has reached a point where its most reliable theories meet conditions they were never designed to fully handle. General relativity excels at describing smooth space-time and large-scale structure. Quantum mechanics excels at describing microscopic systems and information. When gravity becomes strong and quantum effects cannot be ignored, both descriptions strain. What remains open is not whether this tension exists. It clearly does. What remains open is how nature resolves it. One unresolved question concerns the microscopic structure of space-time. If space-time has entropy, then it must have underlying degrees of freedom. But no experiment has revealed what those degrees of freedom are. No observation has detected discreteness in space or time. At accessible scales, space-time appears smooth. This does not rule out microscopic structure. It only tells us that if it exists, it lies far beyond current experimental reach. Another open question concerns emergence itself. In known physical systems, emergence comes with clear limits. Thermodynamics emerges from atoms, but it breaks down when systems become too small. Hydrodynamics emerges from molecules, but it fails at very short distances and times. If gravity is emergent, then there must be regimes where the emergent description fails. What those regimes are, and how they would appear observationally, remain unknown. A related question concerns universality. General relativity works astonishingly well across a vast range of scales and conditions. Any emergent explanation must account for this robustness. It must explain why the same geometric laws appear everywhere they have been tested, without fine-tuning. This requirement is more restrictive than it first appears. There is also the question of time. If the arrow of time emerges from entropy, then why did the universe begin in such a low entropy state? Gravity complicates this question. because gravitational systems behave differently from ordinary thermodynamic systems. Clumping increases entropy, even as matter becomes more structured. Why the early universe had the conditions it did remains one of the deepest puzzles in cosmology. Information raises its own unresolved issues. While theoretical models suggest that information is preserved even in the presence of horizons, no direct observation confirms how this happens in real black holes. The radiation emitted by black holes is extraordinarily weak for astrophysical objects, making direct tests effectively impossible with current technology. This leaves the information problem in a curious position. It is theoretically constrained, but experimentally inaccessible. Another open question concerns the role of observers. Horizons, temperature, and entropy often depend on what an observer can access. Accelerating observers see thermal effects where inertial observers see none. This observer dependence raises subtle questions about what is objective and what is relational in physics. These questions do not undermine established theory, they reveal its depth. What ties all of these open issues together is a shared theme. Gravity does not behave like a simple force. It reshapes the concepts that physics relies on. Space, time, entropy, and information stop being independent ideas and begin to merge. This merging suggests that the next step in understanding gravity may not come from modifying existing equations, but from rethinking what the equations are describing. At this stage, physics does not know which direction that rethinking will take. Multiple approaches are being explored. Some focus on quantum geometry, others focus on information theory, others seek entirely new mathematical frameworks. What they share is caution. None of these approaches claim experimental confirmation. None claim to have replaced existing theories. They exist because the problem demands exploration, not because a solution has been found. This openness is not a weakness. It is a reflection of how physics advances when it reaches its limits. The absence of a final answer does not mean the question was wrong. It means the question is deep, and gravity has proven again and again that it is deeper than it first appears. As these open questions remain unresolved, one pattern stands out. Every attempt to understand gravity at a deeper level ends up confronting the same set of ideas: information, entropy, limits, and the strange way space-time responds when those limits are approached. This repetition is not accidental. It suggests that gravity is not just another phenomenon waiting to be explained with slightly better tools. It is pointing toward a structural feature of reality that current theories only partially capture. One such feature is the apparent universality of entropy bounds. No matter how different the physical systems are, gravity seems to enforce the same restriction. Try to compress too much information into a region, and space-time reacts. Horizons form. Access is limited. The details of the system no longer matter. Only the boundary does. This universality is striking because it does not depend on the specific matter involved. It does not care whether the information comes from particles, fields, or radiation. Gravity responds only to the total content. That kind of indifference is rare in physics, and it usually signals something fundamental. Another recurring theme is the role of correlations. In quantum mechanics, information is not stored in isolated objects. It is stored in relationships. Entanglement binds systems together in ways that cannot be reduced to their parts. When gravity is involved, these relationships appear to shape geometry itself. This raises a difficult question. If space-time geometry reflects patterns of information, then geometry is not primary. But if geometry is not primary, what replaces it as the foundation of physics? At present, there is no agreed answer. Some approaches suggest that networks of quantum correlations are fundamental and that space-time emerges from them. Others suggest algebraic structures with no direct geometric interpretation. Still others suggest that the familiar notions of space and time are approximate descriptions that break down entirely at the deepest level. What unites these approaches is restraint. They do not claim to describe reality directly. They aim to be consistent with what is already known, while extending it cautiously. This caution is necessary because the cost of being wrong is high. Gravity is not an isolated phenomenon. It influences everything from the behavior of clocks to the evolution of the universe. Any foundational mistake would ripple outward. There is also the question of testability. Physics, ultimately, relies on observation. Ideas that cannot, even in principle, lead to observable consequences remain speculative. Many of the deepest questions about gravity, entropy, and information lie far beyond current experimental reach. This does not mean they are meaningless. It means their status must be stated clearly. Some ideas may never be testable directly, but they can still guide theory. Others may lead to indirect signatures, subtle deviations from established predictions. Identifying those signatures is an active area of research. For now, however, the situation remains unchanged. General relativity continues to describe observed gravitational phenomena with extraordinary accuracy. Quantum mechanics continues to describe microscopic systems with equal success. The bridge between them remains incomplete. The open questions are not about whether these theories work. They are about how they fit together. Gravity has exposed the seams. It has shown that space, time, entropy, and information are not separate chapters in physics, but intertwined elements of a single unfinished story. Understanding one requires understanding the others. This recognition does not close the book. It leaves it open, with pages still to be written. And that openness, uncomfortable as it may be, is exactly where physics is meant to be when it approaches the limits of what it can currently explain. As the picture remains unfinished, it is tempting to search for a single missing piece, one idea that would suddenly make everything fall into place. History suggests that this expectation is rarely met. Deep problems in physics are not solved by one insight alone. They are resolved when many partial insights converge into a new framework. Gravity appears to be such a problem. What makes it different from earlier revolutions is not just its difficulty, but its reach. Questions about gravity are no longer confined to motion or force. They extend to the meaning of space, the nature of time, the role of information, and the limits of what can be known. Each of these concepts has been stable on its own. Gravity forces them to interact. This interaction has revealed something important. The frameworks that work so well in isolation may not be fundamental on their own. General relativity may describe space-time accurately without explaining its origin. Quantum mechanics may preserve information perfectly without explaining where space-time comes from. Entropy may explain irreversibility without explaining the structure that allows it. None of this diminishes their success. It reframes it. In this light, the absence of a complete theory of quantum gravity is not a failure of imagination or effort. It is a sign that the problem requires a deeper shift in perspective, a shift away from treating space and time as givens and toward understanding them as outcomes. Whether that shift ultimately leads to emergence, to new symmetries, or to entirely unfamiliar mathematics remains unknown. Physics has reached the edge of its map, where directions are no longer clearly marked. What can be said with confidence is that gravity has earned its reputation as different, not weaker, not stranger in behavior, but different in what it demands from explanation. It refuses to be treated as just another interaction. It forces physics to confront the limits of description itself. That confrontation has already changed the field. It has reshaped how black holes are understood. It has elevated information from a bookkeeping tool to a physical principle. It has connected entropy to geometry in ways that were once unthinkable. These changes did not solve the problem. They clarified it. And in physics, clarity is often the most valuable progress of all. As long as gravity continues to resist complete unification, It will continue to serve this role. A guide that points not toward easy answers, but toward deeper questions. Questions that remain open not because they are poorly formed, but because they touch the foundations of how reality is organized. That is where the story stands. Not at a conclusion, but at a horizon of understanding. After following gravity through geometry, entropy, information, and time, the final task is not to offer a dramatic conclusion. It is to be precise. Precision, not certainty, is where physics earns its authority. There are statements physics can make with confidence. Gravity, as described by general relativity, is not a force in the ordinary sense. It is the manifestation of curved space-time, and this description has been tested across an enormous range of conditions. From falling objects to orbiting planets, from bending light to colliding black holes, the theory works. No alternative description has matched its empirical success. Entropy is not a metaphor. It is a rigorously defined physical quantity that counts microscopic possibilities. It explains why macroscopic systems behave predictably, why time appears to have a direction, and why certain processes are irreversible. These facts are not speculative. They are foundational. Black holes obey thermodynamic laws. They have temperature. They have entropy. That entropy scales with surface area, not volume. This result is one of the most striking and reliable outcomes of combining quantum theory with gravity in a controlled way. Information is conserved in quantum mechanics. This principle has survived every experimental test. Any theory that discards it must explain why quantum mechanics works as well as it does everywhere else. From these established results, physics can responsibly say something more. Space-time is not a passive backdrop. It participates in physical bookkeeping. It responds to information limits. It behaves in ways that resemble thermodynamic systems under extreme conditions. Physics can also say that current theories are incomplete. General relativity does not explain the microscopic origin of space-time. Quantum mechanics does not explain how geometry arises. Entropy connects these theories, but does not yet unify them. Beyond this point, physics must slow down. It is consistent with known evidence that space-time could have microscopic degrees of freedom. It is consistent that gravity could be an emergent phenomenon, much like temperature or pressure. It is consistent that geometry could arise from deeper informational structures. But consistency is not confirmation. No experiment has shown that space-time is emergent. No observation has revealed the fundamental constituents of space or time. No measurement has demonstrated that gravity is an entropic force in nature. Holographic models show that emergence is possible in special theoretical settings. They do not prove that the universe operates this way. Entropic gravity proposals show that some gravitational behavior can arise statistically. They do not reproduce all known observations. These ideas remain active because they address real tensions, not because they are settled. This distinction matters more than any individual result. Physics does not advance by replacing uncertainty with confidence prematurely. It advances by mapping where certainty ends. That map is now clearer than it has ever been. Part 2. What gravity has ultimately forced physics to confront is not a missing equation, but a deeper question about explanation itself. For centuries, physics progressed by identifying fundamental entities and forces, particles, fields, interactions. Space and time were assumed. They were the stage on which everything else played out. Gravity disrupted that pattern. By tying itself to space-time, gravity made the stage dynamic. By producing horizons, it introduced limits on access and information. By obeying thermodynamic laws, it linked geometry to statistics. Each step eroded the idea that space and time are simply given. Entropy sharpened this disruption. It revealed that large-scale behavior often hides deeper microscopic rules. It showed that direction, irreversibility, and even causality can emerge from probability rather than being imposed from the start. Information theory extended this insight. It showed that correlations matter more than objects. that what can be known depends on structure, not location alone. Together, these ideas suggest a shift in how physics may ultimately describe reality, not as objects moving through space, but as information organized in consistent ways. Geometry, force, and time would then be consequences, not inputs. This is a powerful vision. It is also unfinished. Physics has seen visions like this before. Some led to revolutions. Others faded. The difference was never philosophical appeal. It was evidence. For now, gravity remains exactly as general relativity describes it wherever it has been tested. Dark matter remains the simplest explanation for many observations. Quantum mechanics remains unchallenged in its domain. At the same time, the conceptual pressure has not gone away. Black hole entropy still demands an explanation. The information problem still constrains theory. The smoothness of space-time still raises questions when viewed through a quantum lens. These pressures ensure that the search continues, not with declarations, but with restraint. Not with final answers, but with sharper questions. Part 3. The most important outcome of this journey is not a claim about what space-time is, but a clearer understanding of what physics is allowed to say. Gravity may be emergent, or it may be fundamental in a way that has not yet been recognized. Space-time may arise from information, or information may require space-time to have meaning. Time may be a statistical phenomenon, or it may remain basic. At present, none of these possibilities can be ruled out. None can be confirmed. What can be confirmed is that gravity is different, not because it behaves unpredictably, but because it forces physics to confront its own assumptions. It exposes the limits of familiar concepts. It reveals where description gives way to deeper structure. In that sense, gravity has already done its work. It has shown that explanation has layers, that what feels fundamental may not be final. That understanding reality is not just about adding detail, but about knowing when to change perspective. This is not a failure to conclude. It is the correct place to stop. Physics does not promise comfort. It promises clarity where clarity is possible, and honesty where it is not. For now, clarity ends at the boundary between established theory and deeper speculation. That boundary is not empty. It is rich with structure, constraint, and possibility. And it is there, at that boundary, that gravity continues to point. Gravity has a way of forcing physics to question things it once treated as settled. For a long time, space and time were not part of the problem. They were the backdrop. Events happened in space. Processes unfolded in time. The job of physics was to describe what moved, not the stage on which it moved. General relativity changed that by making space-time dynamic. Geometry was no longer fixed. It responded to energy and momentum. It could bend, stretch, and form horizons. Space and time were no longer passive. They became physical. Entropy pushed this shift even further. Entropy showed that large-scale laws can emerge from deeper, microscopic behavior. Temperature feels fundamental until you learn it is a statistical effect. Pressure feels like a force until you realize it reflects countless molecular collisions. These ideas did not weaken physics, they unified it. When entropy appeared in gravity, especially through black holes, it suggested that space-time itself might belong to this same category, not unreal, not approximate, but emergent. A large-scale description that hides deeper rules. Information theory reinforced this suggestion. Quantum mechanics does not describe particles in isolation. It describes correlations. What matters is not where something is, but how it is related to everything else. When gravity enters the picture, these relationships appear to shape geometry itself. This combination forces a rethinking of what explanation means. If space-time emerges from information, then explaining gravity may not be about finding smaller pieces of space-time. It may be about understanding how information is organized and constrained. Geometry would then be the visible imprint of invisible structure. This idea is radical only if one assumes that space and time must be fundamental. Physics has overturned such assumptions before. What makes the current situation difficult is not lack of imagination, but lack of access. The scales at which space-time's microscopic structure would reveal itself are far beyond current experiments. Black holes offer clues, but they do not offer direct measurements. As a result, physics must operate carefully. It can explore mathematically consistent possibilities. It can test internal logic. It can check compatibility with known results. But it cannot yet choose between competing foundations. This restraint is not hesitation, it is discipline. The connection between gravity, entropy, and information is no longer speculative. It is established through multiple independent lines of reasoning. What remains uncertain is how far that connection goes. Does entropy merely constrain gravity, or does it generate it? Does information merely decorate space-time, or does it create it? These questions are open not because they are vague, but because they are precise and unanswered. What gravity has done is narrow the range of acceptable answers. Any future theory must respect entropy bounds. It must preserve information. It must reproduce space-time geometry where it has been observed. It must explain why these features appear so robustly. In this sense, gravity has already guided physics forward, not by offering a final picture, but by ruling out entire classes of wrong ones. And that may be its most important contribution so far. Gravity never announces itself as a mystery. It arrives as something ordinary. You feel it before you understand it. You stop noticing it long before you question it. And yet, when physics follows gravity carefully, it keeps running into the same edge. Space stops behaving like a container. Time stops behaving like a clock. Information stops behaving like a detail. What once felt solid begins to look relational. What once felt fundamental begins to look statistical. Not imagined, not symbolic, measured, calculated, enforced by limits that appear again and again. Black holes do not explain everything, but they refuse to let certain questions go. They force entropy into geometry. They force information into horizons. They force physics to admit that space-time carries bookkeeping. It does not know how to count. Nothing here requires belief. Nothing here requires speculation. General relativity still works. Quantum mechanics still works. Thermodynamics still works. The problem is not that these theories fail. The problem is that they overlap. And in that overlap, something new appears. Not answers, constraints, limits on information, limits on access, limits on how much space can contain. Those limits do not tell us what space-time is made of. They tell us that space-time cannot be everything it appears to be. That is the quiet shift. Gravity may be fundamental, or it may be emergent. Space-time may be primary, or it may arise from structure beneath it. Physics does not yet know. What it does know is this. Whenever gravity becomes extreme, entropy appears. Whenever entropy appears, information is counted. And whenever information is counted, geometry stops being free to behave however it wants. That pattern is real. Its interpretation is not settled. And so the story does not close with an answer. It closes with a boundary, a place where explanation slows down, where language becomes careful, where certainty gives way to structure. Gravity does not tell us what reality is. It tells us where our descriptions stop.